Welcome to our seminar about object tracking, and I'm Duc Anh, who will be the speaker of today. Okay, so first we'll go through main content of the seminar, which is what is object tracking, types of object tracking, and I will talk about some main algorithms such as sort, deep sort, for MOT and bike track, and we'll go through some applications of object tracking. Okay. Wait for me for a few seconds. And then we create a unique ID for each of the initial detections. And then after the association of the objects, we track each of the objects as they move around frames in a video or a live camera, maintaining the ID assignment. Next, we'll go through the types of object tracking. First is single object tracking, which focuses on tracking one specific object within a video frame. This object is typically identified or initialized in the first frame, and the tracker continues to follow it through subsequent frames. The next type is multi-object tracking, which extends SOT to multiple objects within a scene. MOT algorithms must handle the complexities of multiple objects interacting with each other, overlapping or occluding one another. And there are two inference methods for object tracking, which is online and offline tracking. Online tracking is for real-time tracking, which only uses the current frame and the frame right before in order to track objects, which keep the online feature and speed to keep up with the real-time video stream. Yeah. And offline tracking uses all the frames of the video, which ensures higher accuracy for tracking methods. Okay. So next, we'll go around the main procedure of object tracking, which first the input it is a sequence of frames of video. Next, we will take the frames to an object detection model, which can be convolutional model or something else, so that we can get the detection of the object, like a mask or bounding box, etc. So, and then we continue on object tracking, which can be used by many algorithms. Okay. And next up, I will go through some of the most famous algorithms so that we can have a look at how they work. Okay. First, we'll go about sort, which is simple online real-time tracking. Okay. This is a pipeline of sort, which goes from the detections, and then we use the IOU match on them. The unmatched tracks are deleted, while the unmatched detections are treated as new tracks, and the matched tracks are updated using a Kalman filter, and all of the tracks are predicted using a Kalman filter. And next, on the next frame, they are also getting in an IOU match. Okay. Next, we'll go through the main algorithm of sort, which is Kalman filter. Okay. So the main thing that we are using here is a state, a time step k, or the measurement at the time step k. Okay, xk is calculated using the state transition matrix to transit from the previous state to the current state, which is also added by a noise of the process at the time step. And zk is a measurement at time step k, which is calculated by a measurement matrix and also added by a measurement noise. Yeah. Okay, so let's take the original variable of the sort problem, yeah, which is the x, y, s, r, and x dot, y dot, and s dot, which is the first two variables are the center, are the location of the center of the bounding box, which is x and y. S is the size of the bounding box. Usually it is the height, and R is the ratio of the bounding box, and X dot, Y dot, and S dot are the speed or velocity of the three variable. So as like normal velocity problem, we can see that the first three variables can be calculated like this. Xk equals to xk minus 1 plus xk minus 1 dot on the delta time. Okay. So that we can contribute the F matrix here like this, which ensures that xk is equals to xk minus 1 plus xk minus 1 dot, yeah, times dt times the difference of time plus the noise. Yeah. Okay. And the measurement matrix could also be calculated using the measurement matrix like this. So we can see that xk, I don't really, okay. We can see that the measurement variable here can be calculated using xk, yk, sk, and rk. Yeah. Okay. So the main target of common filter is to predict and update the measurement so that your future predicts can be as close as possible to the actual measurement. Yeah. Okay. As we can see here, that the state ahead is calculated using is xk equals to a x hat k minus 1 plus b uk, which is pretty the same as this. However, we have a B matrix, which is a control matrix, in order to control how your model predicts the future states. Okay. And the input is also kept in the error covariance ahead, which is PK here is also calculated using the state transition matrix minus multiplies with PK minus 1 and the A transpose of the matrix A plus Q, and Q here is a process noise covariance. Okay. And the Q matrix is often defined as a matrix with the same size as PK, which and goes from a Gaussian distribution. Yeah. Okay. And after we predict the future state, we also update the measurement, which is used by computing the Kalman gain. Okay. And the Kalman gain is calculated by the error of covariance times the measurement matrix. Yeah. Okay. All of them are multiplied by the observation matrix times the error covariance times the transpose of the measurement matrix plus R. R is the measurement covariance that we have seen here. Yeah. Okay. And all of them are divided. Okay. Okay, and they are multiplied by the inverse of this sum. Okay, and next we will update our estimation with the measurements zk that we have calculated earlier using the function xk, x hat k will equal to the projected state ahead plus the Kalman gain multiplied by the measurement zk minus the measurement matrix multiplied by the projected state, and then we will update the error covariance, which is pk equals to, this is the identity matrix. Yeah, equals to the identity matrix minus the Kalman gain times the measurement matrix, all of them multiplied by the projected error covariance. And the update continues. However, sort algorithm lacks the ability to reinitialize the objects that they have detected earlier, but after that they disappear from the scene, so that so deep sort is invented to check to fix. Okay, so this is the algorithm pipeline of deep sorts, which also includes the getting the detections. However, we can see that there are two matching stages which are used in deep sort, and the tracks are separated into um, two types, which are unconfirmed and confirmed. Yeah. Okay. So what does it actually update from sort? Yeah. Okay. Um, okay. So first, it introduces a new a new distance function to associate the frames, the detections with the already detected tracks, okay, which is the Mahalanobis distance, which is used to detect the distance from a point D to the to a distribution which have the mean of yi and the variance of si. Yeah, this can track the difference between detections when they are moving fast, and therefore it could be better than cosine distance to assign the detections into tracks. However, these two distance are used altogether in the algorithm of this sort so that they can re reconfirm the near tracks and also the far tracks that haven't been seen by a specific number of frames so that they can delete it. Okay, yeah. Back to the pipeline. So, okay, the matching cascade algorithm is that they use the matching by separating the tracks in terms of the edge, which in the paper varies from 1 to 30, and then they detect and then they assign the detections and the tracks based on their edge from low to high, and then after that they match the remaining tracks and the mean remaining detections. Okay. After the matching, we can see that the unmatched detections and the unmatched tracks are goes into the IOU match, which is the same as the sort algorithm. Okay. And the unmatched tracks of the IOU match are haven't arrived for more than 3 consecutive frames, and they are noted as unconfirmed and they are deleted. And the confirmed tracks are the confirmed track are divided in also 2 groups, which are the tracks that haven't arrived, which more frames than the max edge, which is in this case 30 frames, and they are also deleted. And the tracks that are less than the max edge is continued to be in the track list of this sort. The unmatched detections of the IOU match are considered as new tracks and is also stored in the track array of this sort. All the matched tracks are updated using common filter to predict to match with the object, and all of them are predicted in the next frame, which confirmed frame are matched directly with the detections using matching cascade algorithm, and the unconfirmed tracks are matched using the IOU match. And this algorithm is better than sort at realizing the tracks which haven't been in the frame for like less than 30 frames. And this ensures that the objects won't be assigned a new ID when they reappear in the frame. And by the by testing on the dataset, they realize that deep sort reassigns IDs less than sort by 70%. Okay. Yeah. So okay, that's deep sort, and let's continue to another algorithm, which is fair MOT. It is fair multiple object tracking. Okay. This also goes in the same pipeline as other tracking algorithms, which is from a detection to tracking. Yeah. And the network of fair MOT is like this, which is they downsample the image to 1/4 of the original size, and then they keep downsampling the image, and they also have upsampling connections and convolutional connections in order to generate the detection and the re-ID head. Okay. And the output of this model have 4 branches, as the paper states, which three of which goes in the detection branch, and one is called the re-ID embeddings. Okay. The heat map branch detects the center of each of the bounding box, which is assigned to each of the objects. As we can see, it's a like blue point here for each of the objects. The box size determines the size of the bounding boxes for each of the objects, and the center offset is predicting the distance and the direction of the offset between the detected center and the real center of each of the objects that they have detected. Okay. Okay. So for each ground truth box, they take like 4.4 values for the 4 points of the bounding box. So they compute the object center as Cx, which is equals to x1 plus x2 divided by 2, and the center y is equals to the y1 and y2 divided by 2 respectively. Then its location on the feature map is obtained by just dividing by the stride, and in this paper they set the stride by 4, and by that we can see that the encoded image is 1/4 of the original image. Okay. Yeah. Okay. Yeah. And then MXY is the heat map prediction of of the paper, we can see that it is equals to the total of the exponential of x minus cx squared plus y minus cy squared divided by the standard deviation of the center squared. And this is the heat map value for the point x and y. Yeah. And if the value of this is near to 1, the point has a high chance to be the center of an object. Yeah. Okay. And next is a size detection of the box, which is calculated by x2 minus x1 and y2 minus y1. Yeah. And the offset is calculated as the cx divided by 4, cy divided by 4, minus the floor function of that value, which is also cx divided by 4 floor and cy divided by 4 floor. Okay. And next is the and the re-ID branch will be a convolutional layer which extract the features of the image into a 128 layer feature map. Yeah, that which is stated in the paper. Okay. And the loss of the heat map is taken like the loss of logistic regression, which is also is implemented with focal loss, which is the sum of 1 minus the map xy square powered by alpha, which natural logarithm of xy, and it's also if the point is the center of an object and is equal to 1 minus mxy power b multiplied with mxy powered by a, and with the logarithm of 1 minus mxy. And the loss of the bounding box detection and the center offset detection is the sum of the offset and the size of the bounding box, which with the true bounding box, and lambda is an learnable parameters. Okay. Yeah. And the loss of the identity. Okay. Yeah. Loss of the identity is detected by something else, which is after that we detect the feature, extract the feature map, we then use a softmax layers to map the class, to map the image, to map the detections to a to a class distribution vector which have the probability of each class is pk. Yeah, and then we denote the one-hot representation of the class label is ly of k, and then loss of the identity is the sum of I to n and k to k of the sum. This is a sum of log pk multiplied by the one-hot encoding of the class representation, which is increased by each of the by each of the class that they are that they have failed to detect. Okay, and then loss of the detection is calculated by loss of the heat map and the loss of the bounding box, while the total loss is calculated by a half of the 1 divided by the exponential of W1 and 1 divided by the exponential of W2. And these two are multiplied by the loss of detection and loss of identity, and W1 and W2 are learnable parameters that can be used to balance between the two losses. Okay.
Sorry, I have a question.
Okay.
Fair MOC performs detection and tracking at the same time, right?
This is only for the like detection method, and the association method, like tracking, this paper uses deep sort also.
So okay, so fair MLT is for detection. It's all about detection.
Most of the papers they use deep sort or some other kinds of association, and like most of the things that they increase is what they select for association, or they increase the like accuracy of the detection method. Most of them use Kalman filter to update and predict the future states of the detections.
Okay, so is it true if I understand that fair MOT just introduced new method for detection algorithm, and for the tracking part they use deep sort?
It could be understand it like that, because most of the here the fair MOT paper states that they are not following this sort. It's my fault. However, they follow another paper for their hierarchical association method, which is used to associate detections to the tracks that have been present in the frames. Yeah.
Okay, so the tracking part they use the method of another paper.
Yeah, and personally, when I read that, I think that all of them are like pretty the same. They do not differ a lot from each other.
Okay. Okay. So if fair MOT is not trained for tracking object, so what is loss? So what is identity loss? It
Yeah,
it's like class.
identity. Yeah, it's like the class loss for the fair MOT model.
Okay. But why they do not use the word class? Instead, they use re-ID. They use
Yeah.
re-ID. There is a re-ID module in the architecture.
Yes.
Can you back to the architecture?
Yeah. Okay.
So the input of re-ID embedding of the re-ID embeddings is the object which was already cropped, right? Or the full picture.
They use they use the output of the encoder decoder network to as the input of re-ID embeddings.
What is output of encoder decoder network?
Yeah. Okay. It is the final layers of the encoder decoder network,
Okay.
which is okay. Yeah.
Okay. Okay.
The
Thank you.
output. Okay. Okay. Yeah, and next we will go to ByteTrack, which is considered the state-of-the-art method for object tracking. Yeah, from 2021 to around 2023, and I think that by the beginning of 2024, it is still considered that it is pretty much the state-of-the-art model using for the multiple object tracking datasets. Okay, so what backtrack actually do is instead of removing all of the detections with low low confidence score, like when we are working with object detection, we usually just concentrate on the objects which have high confidence score, like this woman, which remains her confidence score by a score of 0.9 for all of the 3 frames. And we usually like detect this or this guy which have the confidence score of 0.1 as a not of non object or something else like that. And we usually remove them from the tracking algorithm. And what ByteTrack do is they consider all the high or low confidence score objects as trackable objects. And that's what makes ByteTrack the state of the art algorithm in 2021. Okay, so let's see um, the data association method of byte, which is the main algorithm of byte track. Yeah. Okay. The input is a video sequence, the object detector, and the detection score threshold. For each of the detections, the steps are remain the same, which is after we detect, we associate the detection to tracks, and after that we use Kalman filter or something else to predict the track in the next on and on frames. Yeah. And what backtrack actually do is if if the confidence score of the detections is lower than their threshold, they will actually also save that into an array, and which they also assigns to a new track. Yeah. And all of the detections that have low confidence score is also associated to the tracks. Yeah. And these two association methods have different similarity method. Okay. The first one is the first, which is the high, which is a high confidence score detections, can be calculated using the intersection over union similarity or the re-ID similarity, which have been introduced by FireLT. However, the similarity number two, which is about the detections that have low confidence score, the paper states that IOU is the best method to associate the remain tracks and the detections that have low confidence score. And yeah, okay. And this is the assign method of bytes, and the object detector and the tracker like Kalman filter, FireLT, or many else. They can use any tracker and any detector as you like and still get pretty the highest score among all the methods used. Yeah. Okay. To 9 different state-of-the-art trackers on the MOT 17, which is the multi-level object tracking of 2017 validation set. Okay. Yeah. And as we can see that every time we apply the byte method, the association metrics are increased by at least 0.3%. However, there are some cases that the score decrease, but we can see that the most of the time the score increase, and as a result, we can see that by track method is pretty sure a simple but great method. Okay. Yeah. Currently, PyTrack is only the second most most have the second most accuracy amongst the trackers in the MOT17 dataset. However, it is still a great method to apply in case of its simplicity and easy to apply. Yeah. Okay. And on the applications of the tracking, it can apply for traffic cameras, conference meetings, videos, recordings, etc. And it's currently being adopted everywhere in the world. Okay. And that is the end of my presentation. Thank you for your attention. Any questions?
I have a question. So
Okay.
you previously stated that these model, one of these model were the soda of 2021.
Yeah.
Yeah. So since then, are there any other models? Like I heard that Sam 2 just released recently, and I tried it and it works pretty okay. So do you have any comments on more recent models?
Yeah. Mm, okay. Currently, that we are having many sequence like yeah. Um, I have just found some uh, pretty exciting papers for us to like dive in. Okay, let's share this. Okay, this is the currently a SOTA in the MOT17 benchmark dataset. Yeah. And as we can see, by track has gone pretty far. Yeah. Okay. So let's see. Yeah. And this short on tracking method has just been released in July 2024 and is just a preprint. Yeah. Yeah. As we can see, um, feature sort is currently the state-of-the-art model in the MOT17, and MOT 20 datasets, and which we can see at the benchmark right here. You can find pretty much of the um, most high efficient model here, and I think that by applying them, you can get pretty much good results of what you are finding. Mm.
Can you move back to the slide?
Okay. Mm, yeah. Let's see. Okay. Um, which uh, which slide do you have a question?
Can you move to the slide with the loss function of deep sort?
Deep sort. Okay. You mean this? Oh, this is only distance for the.
Oh, it's my mistake. It's fair
Okay.
MOT.
Okay.
Can I ask a question?
Yeah.
Does idea of using both high confidence and low confidence object track both low confidence and high confidence object threaten the real-time task in using the by track in real-time task tracking?
Okay. Hmm. Um, okay. Like it depends, and the like what the publication of ByTrack does not like publish about their runtime. However, I think that with the source code being published, we can test it by ourselves. Okay here. Um, we we pretty can track on real-time videos with 30 FPS, 30 frame per second. Yeah.
Okay, thank you for your question. for your answer.
Okay. I have a question. So when these two baseline, they capture the object in a frame and assign an ID to each object. So do it store in anywhere, file database, and when the object appeared in another frame, maybe from a different camera, so we will know, or it's just a real time and it's just on one frame only.
Oh, okay. The problem of having the object appear in another camera is typically another type of object tracking, which is multiple camera tracking. And in this seminar, we have only talked about single camera tracking. However, with single camera tracking, if the object disappears and then reappears in another frame, the like this sort, and most of the others tracking methods, they store 100 nearest tracks feature maps so that they can match with the re-detected object as fast as possible. And they store them in a buffer memory without using any data sets. And obviously, I think that using data sets is pretty a great choice. However, you have to treat the real time to ensure that the dataset queries are used correctly. Is that okay?
Give it answer. Yeah. So another question. So this kind of object tracking keep the last state of an object in a frame, right? The last state or a sum of the state.
It like in each frame that they detect, they store that track in the memory. Like the most recent tracks.
Okay. Okay.
I have a question. So, when there are a lot of similar objects, like a herd of horses, for example, and they may get overlapped, so do these models, can these models handle that situation? That's
It is based on wait, and that is the problem which most models before backtrack get, right? If they have the low confidence score, like when they are overlapping with each other, you see, they get deleted. So before backtrack, if whether they can the ability of the models to like maintain the detection are a little bit lower. However, deep sort also can also maintain that the tracks are properly detected by the Kalman filter predict and update. Yeah. However, it is not that like it is not that efficient. As I have by myself tested deep sort on a video. Yeah. Any more questions? I think that this topic is pretty great for us to like research. Yeah, and it has still has room for improvements as more new papers are published every day. Okay. Anyone have any questions? If not, we can see the newest paper, which is feature sort. This is only and not only, but is an upgraded version of these sorts, and it is literally the state of the art method for the MOT17 dataset right now. I think that based on this, we would really have some room for improvements in our model. Any more questions? Or we can start the meeting here.
So what makes feature sort different from deep sort?
Okay. Yeah. It is first. It use a stronger detector. Yeah. Stronger detector makes the model will can detect objects better. And next, they use feature-based models for both re-ID and tracking consistency. Yeah. They use a color annotation process for the image into 10 categories, and they also encode the colors as a vector. Yeah. They also encode the color style and direction. Altogether, you can pretty assume that they use pretty much of the feature of an object or the whole image in order to track each of the objects that they have detected.
So they are using YOLO to detect as their detection model. Is that
Yes.
true? But
Yes.
like YOLO have to be trained on a data set. So how many classes does that YOLO model can detect? And what if the object that we want to track is something outside of the data set that the detection model was trained on?
Okay. I haven't read this thoroughly, so the dataset they use in for training the YOLO model is a combination of like 7 datasets, which is relatively huge, and currently that the dataset they're testing is based on all of these datasets. Yeah. However, I think that besides of that, they doesn't have any loss function for the IDs, like the classes of the objects. So I think that whether a new object is present doesn't necessarily mean it the pres like the performance of the model will be decreased. We can you can find more about this topic. Any more questions? Okay, so I think that my presentation will end here. Thank you for listening.